Hi, it's Mr. Anderson. Today I'm going to be talking about water. I love this picture of a water droplet. The forces that hold this water droplet together are the same forces that allow us to survive. And a neat thing about water is that wherever we find water on our planet, we also find life. And so it's very important. And so this podcast is dedicated to water. Okay. First of all, what do we mean by a polar molecule? Well, oxygen is unique, and oxygen is unique in that it is almost the most electronegative atom on the whole periodic table. So in other words, it gets second place. The most electronegative is actually fluorine. Fluorine can even form compounds with some of the noble gases, which is pretty amazing. First of all, we should talk about what electronegative actually means. Electronegative means how much you want electrons. And so if we think about the valence electrons of oxygen, oxygen, remember, has 6 valence electrons. It would love to have 8. And so if it can just gain 2 more electrons, then it can be happy. And so if we look at this down here, so right here we've got an oxygen attached to 2 hydrogen atoms. Oxygen's highly electronegative, and so what it's going to do is it's actually going to share electrons with hydrogen, and so it's not going to form an ionic bond, but it's going to share those so unequally that it's really a polar molecule. What does that mean? It means that on one side of the molecule, so on this oxygen side, it's actually going to have a negative charge over here, and then on the other side it's going to have a positive charge up here. So we get a positive charge up here. And as a result of that, the whole molecule has a charge. And a good way to think about how that works is it's almost like a magnet. And so if a magnet looks like this, and it's got this north and this south, water's going to behave kind of the same way. And so let's talk about how that actually works. The most important bond that we need to talk about when we're talking about water is what's called a hydrogen bond. And so I have a little model for a water molecule right here. And so the red represents the oxygen and the white represents the hydrogen. And so if we were to look at this bond right here between the hydrogen and the oxygen, we'd call that a polar covalent bond. But these ones are special in that they have little magnets inside them. And so if I try to hold it so the 2 hydrogens are next to each other, you'll notice that they'll repel each other. In other words, they'll push each other apart. So it's hard for me to get them to stick together. But if I hold the oxygen next to the hydrogen like that, there will be an attraction. And so that attraction between the hydrogen on one side and the oxygen on one side is called a hydrogen bond. It's much weaker than the actual covalent bond between the hydrogen and the oxygen, but what it does is it holds that water molecule together. And so if it's water vapor and it's shooting around, there's not going to be much attraction. But when we get liquid water and the water is flowing around itself, we actually get these hydrogen bonds that hold it together and give it that property of cohesion. And so if you think about hydrogen bonds, and we'll see hydrogen bonds in like ammonia as well, sometimes with nitrogen, but usually what a hydrogen bond is an attraction between a hydrogen on one side, which has a positive charge, and an oxygen on the other side, which has a negative charge. And so in this diagram right here, this would be a hydrogen bond right here. Hydrogen bonds are really important in holding water molecules together, but they're also important in biological life. In other words, the DNA, the 2 helices, or the 2 sides of the double helix, is actually held together with the hydrogen bond. Okay, polar versus nonpolar. I have 2 things on this slide that are polar. So this would be water on this side. These are water molecules. And you can see that the water molecules are kind of lining up. So we get that hydrogen bond between the hydrogen on one side and the oxygen on the other. This would be a fat. And so this would be like an oil, like an olive oil would be mostly made of this triglyceride that looks like that. So what is this made up of? Well, you can see that we got a little bit of oxygen up here, but most of it is actually carbon. And so carbon is making up most all of this fat. Now carbon is not highly electronegative, kind of fits somewhere in between the 2. And so this whole molecule, this fat molecule, is a nonpolar molecule. And you've probably noticed other things that are nonpolar like oil or gasoline. If you pour them into water, they don't mix. And the reason why is that water has a charge, and so it's only able to grab onto parts that are also charged. And so you might be a little confused with polar and nonpolar, but a way that I always remember this is that like dissolves like. And so if you want to break down something that's charged, then you should use a charged particle. If I want to break something down like fat, what am I going to do? I'm going to have use something that's nonpolar to break that down. So I've come up with 5 properties of water that are important just based on it being a polar molecule. First one is called the high specific heat. High specific heat is a measure of how much energy you have to put into a molecule to actually change its temperature. And so remember, temperature is the speed of those molecules as they move around each other. And it's way easier to heat up something like alcohol. And the reason why is that alcohol doesn't have much of these hydrogen bonds, and so it's not held together, so it's easier to heat it up. A real-world example, I'm actually in West Yellowstone right now at a ski. My kids are at a ski camp, but we're just skiing down here. And this is the temperature in West Yellowstone. This is the temperature last night was negative 22 degrees. And so that's pretty darn cold. Now, if we were to go straight across as far as latitude, we'd end up in Seattle. And Seattle weather right now is going to be much nicer than it is in Yellowstone. And the reason why is that Seattle's sitting right on the ocean. And as that ocean absorbs energy during the summer, it doesn't change much because water has a high specific heat. And likewise, during the winter, when it cools down, it actually is giving off some of that energy. And so it keeps Seattle fairly temperate. And so high specific heat of water, it explains why it takes a long time for water to actually boil when you put it on a stove. Okay, next thing that's important as far as these properties go is that since it's a polar molecule, it's a really good solvent. And a solvent, remember, is something that breaks down a solute. And so I love this diagram right here. What we have is sodium chloride, which is just regular table salt. And that's an ionic compound. Remember, we have these cation sodium ions and these anion chlorine ions. And so what happens with water, if we look right here in the middle, is that chlorine is actually surrounded, since it's a negative charge, it's surrounded by the positive hydrogen atoms. And so they'll circle around that ion, and likewise the sodium, which has a positive charge, is surrounded by the negative oxygen atoms. And so water works as a really, really good solvent. And in fact, that's why we're filled up mostly with water. It keeps our heat the same, but also it moves nutrients around. It's really good at that. Next, we have cohesive properties. Okay, so water, remember, is held together by this hydrogen bond. And so if we have a group of these molecules, they'll all be held together. And so we get these cohesive forces holding the water together. And so in this picture right here, we've got a paperclip that's actually floating on water. So water has a high surface tension. And the reason why is if we were to look way down here, there's these cohesive forces between the water molecules. And it almost works like a skin, giving surface tension to that surface of the water. Next one would be capillary action. Capillary action works like this. If you have one water molecule attached to another water molecule, you can get this long string of water molecules like this. And so how does water get to the top of the tree? The way it works is you'll evaporate one water molecule at the top, and as we lose that, the water will flow up, and so we have this long flow of water molecules moving all the way up a tree. So that's capillary action. An example of that, let me try to sketch one out, is if we had a tube, let's say we had a tube that looked like this, and then that tube was just sitting in water. Water's going to start flowing up the tube, and the reason it flows up the tube is the water molecules are attached to water molecules farther down. If I were to make a thinner tube, so let me try to make a thinner tube. Let me try. A thinner tube, the water would actually flow up a larger amount. Or if I were to make a microscopic tube, the water might flow all the way up and even start to flow at the top. And that's called capillary action. And so the microscopic tubules or tubes inside a tree are actually called xylem. And then the last thing is the idea that as water becomes colder, it actually becomes less dense. And so the density of water is 1.0, so that's going to be grams per cubic centimeter. But the density of ice is actually closer to 0.9 grams per cubic centimeter. And that's unlike anything else you can think of. If you've ever played basketball on a cold day, you realize that the gas inside the basketball is actually compressing, and so it's becoming less dense. But water is unlike that. And so the reason why again, is these hydrogen bonds between the water molecules. And so what it does is it creates these beautiful hexagonal shapes, and you'll get these beautiful lattices. And that's why on this picture right here, we've got snowflakes, and those snowflakes are held together by these beautiful, based on hexagon kind of patterns. And the reason why that we see that is, again, those hydrogen bonds. And so water is actually going to have a greater density than ice, because as those water molecules actually start to slow down, they will form these beautiful kind of three-dimensional structures. And so that's it as far as water goes. In the next few podcasts, I'll talk a little bit more about solutions and how they actually break down material. But for now, that's a good introduction to water.